Okay, so welcome back. Today what we're going to do, we're going to fool around with chocolate a little bit. We'll blend this chocolate into our lesson. The chocolate, when we get to it, we're going to want to think about it as isotopes, atoms of the same element, different numbers of neutrons. So we've got pink chocolate isotope, blue chocolate isotope. What we're going to do is we're going to place them into a container where we have those isotopes. So our pink chocolate and our blue chocolate, we'll get back to that in a moment. So specifically, today's lesson has really one specific goal in mind other than a couple of key terms. So let's get at the essence of what those specific goals are. And here we're looking at them. We'd like you to have an idea or an understanding what atomic mass means on the periodic table. There's another value on the periodic table which we did not talk about in our last series of lessons. And we talked about something called atomic number, the number of protons. It identifies what an element is. What we didn't look at is this idea down here, this thing called atomic mass. And we're going to see today, it's a little bit mathematical, but I think after our analogy with chocolate, it's going to make some sense. So the next thing that I'd like you to be able to do is understand where it comes from. Where does atomic mass come from? Well, it comes from data for isotopes. Specifically, how heavy the mass and how abundant, how common. So we'll be looking at those ideas. So a skill is coming. Our practice work that will follow up this assignment will be related to that skill. So let's get underway. So there's this key term. It's called atomic mass units. Atomic mass units, AMU. And that's a way to describe how heavy one atom is compared to another atom. It's not an exact mass unit. So it's not like ounces, grams, pounds, or anything like that. It's what I would call a relative mass. All it does is tell us how much heavier one element is than another. So for example, one element might be 5 times heavier than another, or 12 times heavier. It doesn't tell us 12 pounds, 12 ounces. It tells us relative to other elements, how much lighter or how many times heavier is it? That's what we mean by a relative unit. So on the periodic table where we find this data called atomic mass, it is what we would call a relative mass. Okay, well, what is an atomic mass unit? If we were going to oversimplify, this is one way that it is oversimplified. It's virtually the same mass as either a proton or a neutron. So if we can assume and accept that a proton and a neutron have identical mass, which they don't, they're very, very, very close. They're just not identical. If we can assume that they're very, very, very close, we can say that one AMU is the same mass as a proton or a neutron. Generally, it will get us to the understanding that we need. So some people like to say a definition for it is 1/12 the mass of a carbon-12 atom, because a carbon-12 atom has 6 protons and 6 neutrons. And if they are equal in mass, that means 12 atomic mass units, 12 AMU. Okay, so we're in agreement. It's a relative mass on the periodic table, relative mass for atomic mass. So in nature, the stable forms of carbon that exist, carbon-12 and carbon-13, they would be our 2 forms that would exist. If we look on the periodic table, it shows that carbon has an atomic mass of 12.01 grams. And that 12.01 grams is significant to the work that we're going to be taking a look at. So what we should be curious about is this atomic mass that's listed here, 12.01, is really, really close to 12 AMU, pretty far away from 13 AMU. Let's take a look at our chocolate analogy and see if we can't make some sense of it now. So let's suppose, again, what we have in the container, we have pink and blue chocolate. Let's assume our pink is our carbon-12 and our blue is our carbon-13. So we got a whole collection of them in here. So we're going to grab out a random chocolate. Oh, look, we got carbon-12. We're going to grab out another one, carbon-12. Take out another one, carbon-12. We take out another one. Wow, we're getting all pink. I wonder why that is. So some of you are probably catching on about what's actually in here. Yes, there's blue in here, but very few of them are blue. So imagine that we took this chocolate that is made of mostly pink, right? There's just a few blue in here, and it's mostly pink pellets, and we melted it down. Wouldn't the overall melt still pretty much look pink? Because most of that chocolate is pink. So the analogy is that our pink chocolate represents our carbon-12. Our blue chocolate represents our carbon-13. Very few of the isotopes of carbon in nature are actually carbon-13. Most of them are carbon-12. So what does that mean happens? That means that a random atom of carbon chosen at random ought to have a mass really close to 12 rather than 13, because in terms of percentage, a very great percentage of them are carbon-12, a very low percentage of them are carbon-13. So we call that the abundance data sometimes. So the atomic mass is closer to 12 because it's more abundant than carbon-13. Take, for example, hydrogen. If we looked at the periodic table, you would probably guess by looking at the atomic mass which hydrogen isotope is more abundant, hydrogen 1 or hydrogen 3. Well, the atomic mass is very close to 1, pretty far away from 3. So that stands to reason that hydrogen 1 is probably the more abundant isotope in the natural world, and that would be the truth. Okay, so let's take a look at maybe another way of thinking about it. We'd take a look at lithium. If we count specifically here, there's 1, 2, 3, 4, 5, 6 total parts in the nucleus. So we would call this lithium-6. Well, lithium exists as two isotopes, lithium-6 and lithium-7. What we're about to take a look at is what we call atomic mass, which is a weighted average of the naturally occurring isotopes. It's not the way that you're used to calculating averages. It's what we call a weighted average, and we'll see what that procedure looks like. So what we say here is the most abundant isotope, the one that is more popular in nature, is the one that has the greatest influence on its mass. So lithium occurs as two isotopes, lithium-6 and lithium-7. Notice most of these isotopes have 7 total parts in the nucleus. In fact, all of these do. There's only one lithium-6 isotope. So what would that mean related to atomic mass? Well, the atomic mass, this would be the actual data that scientists have access to. Lithium-6, only about 7.5% of the atoms of lithium are lithium-6. The other 92.5% are lithium-7. So that means the atomic mass for lithium ought to be really close to 7 because most of those atoms are lithium-7. There are some lithium-6, there just aren't many in the natural world. So if we were to take a look at some chlorine isotope data, we kind of get to see why the atomic mass of chlorine is sort of close to 35 and 36. There's 2 common isotopes of chlorine, chlorine-35 and chlorine-37, but most of those chlorine atoms exist as chlorine-35. So like the statement says up here, the most abundant isotope has the greatest influence. The atomic mass of chlorine is closer to 35 than it is to 37 for that reason. So our atomic mass is influenced by how abundant, how popular in nature, indicated by a percentage. The higher the percentage, the more abundant it is, and the mass, how many total parts are in the nucleus. Okay, so here's a hypothetical example about calculating atomic mass. So scientists have access to some equipment. The equipment's called a mass spectrometer. We won't worry about exactly how it works. That might be a lesson for another day. But they have the ability to sort atoms by how heavy they are generally. So what we find out is that, here's our hypothetical example here. The element beryllium was discovered. And what we know is that it has 3 isotopes. Beryllium-13, 89.25% of it exists that way. Beryllium-11, 3.75 exists that way. And beryllium-12, 7% of it exists that way. So we want to use that data to calculate the atomic mass. And that's what I'm about to demonstrate for you, how we go about dealing with that. So let's take a look at exactly how this works. So what we first do is we kind of make a chart. The chart lists what isotopes we have. So there are 3 different isotopes. So we read the words carefully. We have 3 isotopes of beryllium, 13, 12, and 11. The next thing we do is we list the masses. Well, that comes from the mass number, right? The number right after the name of the element. 13 atomic mass units, that means total parts in the nucleus, protons and neutrons. Even though a moment ago we said that's not the exact mass, but that is virtually the way that we can accept it, because protons and neutrons have just about the same mass. So 13, 12, and 11. Next thing we do is we pull the abundance data right out of the words. So in the words, it said beryllium-13 is 89.25% abundant. So I copy that down. I look for beryllium-12. It says that 7% of it is that mass. And then I look for our isotope number 11. It says that 3.75% is that mass. If we take notice, this adds up to 100%. So there's 3 different isotopes that add up to that. The next thing we do is we realize when we deal with percentage, we're not going to use this number 89.25. Here's the reasoning why, folks. 89.25% actually means the number 89. Let's write it out, 89.25 out of 100, which means divided by 100. Well, when we divide a value by 100, something interesting always happens to the value. What happens to the value is the original decimal location between the 9 and the 2 gets pushed over 2 places to the left, and it becomes 0.8925. So we're generally just going to cross out that percentage, move the decimal 2 positions to the left, because that means divided by 100, which is what percent means, for 100. And that's going to allow us to deal with the mathematics a little easier. Okay, so what we're doing is we are recording the percentages in what we would call a relative abundance instead of a percent abundance. We're moving the decimal over 2 times, which is really what percentage means, out of 100. So we're doing that for all 3 of our isotopes. Next thing we do, simple math. We multiply our mass times our abundance for every isotope. What that's going to do is that's going to give me the contribution in mass that comes from each individual isotope. So maybe your teacher told you that 90% of your class grade will come from your test scores and 10% will come from homework. That kind of means that homework's not going to count for that much. So that this takes into account that format. We're calling this a weighted average. So when we look at atomic mass, it's called a weighted average. That's what this mathematics is about. How do we get a weighted average? Well, mass times percentage. Remember, percentage we converted into decimal form. So 13 times 0.8925, we record the value. I like to keep it to about 4 decimal places. We could round with good accuracy later if we needed to then. 12 times 0.07, I think that if we added 2 zeros to the end, that would add the 4 decimal places. 11 times 0.0375. Now we have the mass contribution that comes from each of these. Look at all the mass from the top one and the little bit of mass from the bottom 2. Well, all we really do now is we add up those 3 values and they become the atomic mass that would go on the periodic table. So we're going to add them and we would get 12.855 atomic mass units. So that's what would go on the periodic table for this particular element called beryllium. And the procedure or the process is always the same. So you'd have to know what the mass of every element is and what the percentage abundance is. Multiply mass times abundance, get a contribution, add up all the contributions, you'll end up with the atomic mass. Notice there's no division, even though we're calling this an average. It's a special kind of average called a weighted average. So some things count towards more. go back to the analogy, right? The pink should count for more because there are more pink. In this case, the 13 should count for more because 89% of them atoms have that mass of 13. Okay, let's take a look at some actual data for an element. So here's some actual data for the element chlorine. We read the words. Chlorine 35 and chlorine 37 are the two isotopes. So we list them. Next thing we do, the masses. Well, chlorine 35 has a mass of 35. Chlorine 37 has a mass of 37. The next thing we do, percentages, the abundance data. So we write out the percentage. I'm writing it the way it was written. Excuse me, it looks like we have a little bit of a typo that we should correct before. Okay, we had some incorrect abundance data in our words up here, so we have that corrected. So we look at the data, it says 77.36% abundant for chlorine 35. So we transfer that down. 22.64% abundant for chlorine 37. So before we even start, we know this is going to be closer to 35 than it is to 37 when we get the answer, because most of the atoms, 77% of them, are chlorine 35. Okay, remember what we said, we'll divide them by 100, which means move the decimal 2 positions to the left, and we end up with 0.7736, 0.2264, multiply mass times abundance, mass times our relative percentages, and that'll get a contribution from each isotope. Contribution from each isotope, it's really just the product of multiplying mass times abundance. If you remember what we did with those numbers before, we add them, and what we end up with is atomic mass. No division. Even though it's called an average, it's a weighted average. So if we were to look on the periodic table, we would find out that chlorine has, if you look down here, atomic mass 35.45. We really just generated that using isotope data, mass data, and abundance data. There's only one thing that clouds the issue a little bit, and that is that a proton and a neutron are not identical in mass. That's okay. So if we see an example where that becomes significant, you're going to see something that just looks a little different, but it actually tells you exactly what to do. So this particular example says the mass of a proton and neutron, they're not exactly the same. So what we're going to do is we're going to use exact mass data, which scientists have access to. We're not going to use the mass number. We're going to use an exact mass value in atomic mass units. So we're going to read carefully, and we're going to do the same thing we did before. So let me show you. We read the words. The most common isotope of silicon is silicon 28. So this says there's 3 isotopes, silicon 28, 29, and 30. So if you remember from before, first thing we do is we write down our isotopes. Next thing we do is we get the mass amounts. Now the masses are in exact mass, not in mass number form. Well, that's only because a proton and a neutron are not identical in mass. They're similar, they're not identical. So if we have access to this exact mass data, we should use that. We'll get much more accurate data compared to what's on the periodic table when we have access to exact mass data. Well, look what it says about silicon 28. The exact mass is 27.9769265. Lots of numbers. So we just transfer the data down for each of the isotopes, right? Silicon 29 has this exact mass. Silicon 30, notice how close to 28 this number is. How close to 29 this number is. How close to 30 that number is. That's not a coincidence. Now we look and we read the abundance data, the percentages. 92%, the most common isotope, silicon 28. We'll look at the atomic mass for silicon is real close to 28. That's because 92% of those atoms are that isotope. 4.67%, silicon 29. 3.10%. If we add that up, that makes or accounts for 100%. Next thing we do, right, we convert those percentages by moving the decimal 2 times to the left, which means we've divided the value by 100, which is what percent means for 100. Okay, be careful. We move it twice to the left. It doesn't become 0.467. It becomes 0.0467. We got to be careful of that. We need to move the decimal twice, not once. Okay, so 0.0310. Next thing we do, we're going to get our mass contribution from each element, multiply mass times abundance, use the exact mass data. We'll get a value for silicon 28, a value for silicon 29, and a value for silicon 30. Remember what we did with those? We got 3 numbers, add that mess up. We add it up, we get something super close to what's exactly on the periodic table for silicon. So we have the exact mass data here. That's why we got identical information. When we round to the hundredths place, we get the same value that's found on the periodic table. So today your follow-up assignment will be to calculate some atomic mass information for maybe some hypothetical or some actual chemical elements, knowing that you would have to know what the mass is and what the percent abundance is. So look for those 2 bits of information and how they relate to which isotopes exist. Multiply mass times abundance. Don't forget, move the decimal 2 places to the left for your percentages. When you get your final numbers, your mass contributions, add them up. That'll become what we call atomic mass. So that wraps up or concludes our lesson for today. Until the next time, I'll talk to you soon. Have a good day.